So you're probably weirded out by this piece right here. G of x is defined as being the integral from -2 to x of the original function f. And we're just using a replacement variable t. So back when you first learned function notation, you might have a function like this. That meant that if you plugged in a 2 into that function, you'd just be plugging a 2 into the fraction in here. The same thing is happening here. If you're asked to find out what g of -6 is, you're just going to go exactly through as the formula says. It says take the integral to find out what a g of -6 is. It says take the integral from -2, and then here's where an x is. We're going to plug a -6 in there. Of f of t. Okay, and then since we don't know what f is, we have to use the graph of f to help us understand what this integral is. So to find out what exactly -6 is, we're trying to evaluate this integral. And remember, when you first learned integration, if the lower endpoint is actually a greater value than your upper endpoint, you can switch it to make sense at the cost of a negative sign. Now it's going from least to greatest. And now we won't have any trouble interpreting that graph, okay? Just notice, in order to switch these, I had to bring a negative sign outside. And so this is effectively saying, find the area of f, find the area of this graph between -6 and -2. Isn't that just a pretty little triangle? It's got a height of 5. It's got a base of 1, 2, 3, 4, if I can count right. So base times height times 1/2 for the area of the triangle is 12. Nope, I'm an idiot because the height was 5. So 5 times 4 is 20. 20 times 1/2 is 10. And then we can't forget about this negative sign. That's a -10 for this answer. Okay, this is -10. But you shouldn't do it in your head like what I was doing. Always jot your stuff down so you can keep your thoughts straight there. Let's do g of 3. It's the same exact process, just with a different number. We're going to plug in g of 3 right where it says I'm supposed to put a value in for x. If I'm plugging in 3 in for x, it needs to go 3 up here. So I'll write it out exactly as it said. -2 to 3 of f of t dt. Since we can't directly calculate that, we have to use the graph. So here's -2, and here's 3 over here. So you got to find the area of this guy first. Well, look, that's a semicircle with a radius of 2. So the area of the whole circle would be pi 2 squared. But it's not the area of the whole circle. It's half the area of the whole circle because it's a semicircle. So 2 pi is the area of this guy. And careful, this guy down here, apparently everybody's guys, I'm being sexist here, but this girl over here is a triangle. I just sound offensive. It's a triangle with a height of 2 and a base of 1. So base times height times half. That is an area of -1 because it's below the x-axis. So the whole area between -2 and +3 is 2 pi minus 1. So that's it for part A. Part B says find the rate of change of g at 0. So let's go back up to our definition for what the function is. Fundamental theorem of calculus says that if you're taking the derivative of an antiderivative, it's just itself, as long as that integral is stopping at a variable x. Oh, actually, sorry, this is in terms of x now because you're integrating. You integrate this with respect to x, so it becomes let me say that again. You're integrating this with respect to t, and the variable x is getting plugged in for t, so it will be a function of x when you're done. But since we're taking the derivative of the antiderivative, it brings us back down to the original function, even regardless of what constant we start on. So the derivative at the instantaneous rate of change at 0 is the same thing as if you were plugging in 0 into the original function. And we have that graph. At x equals 0, which is that blurred line right there, the y value we get out is 2. I think that 2 is, yeah, the y value we get out is a 2. 0, 2. So that's our answer for this guy. The rate of change at 0 is 2. So from our results above, we just saw that the derivative of g of x is the original function f of x. So let's use that to help us answer part C. Find all values of x on this open interval from -6 to 3, which I believe is the whole graph, for which the graph of g has a horizontal tangent. Remember, horizontal tangents occur when the instantaneous slope where it equals 0. So the graph up here, way up here, the graph up here, how do I get this stuff out of here? The graph up here is the derivative function of g. So we said we wanted to find out where the horizontal tangents equals 0, so we want to find out where this function equals 0. And at -6 it equals 0, at -2 it equals 0, and at +2 equals 0. But I believe the interval said it was not inclusive. Okay, so we're only going to go with -2, -2, and x equals, for Pete's sake, +2. But this is the first part of the question, where horizontal tangents occur. The second part of the question, it wanted to know whether it was a local maximum, local minimum, or neither of these values. So let's start with this guy. We'll circle him in red. This is neither. I can't spell neither because for the function g of x, we don't know what the graph is, but we just said that this is the graph of the derivative. It's positive to the left, it's positive to the right, so that means the slopes, the function is increasing to the left of this point, and it's increasing to the right of the point. So that's your justification for why that's neither. So let's check this one. The graph of g of x is increasing to the left of it because it has positive slopes, but it's decreasing to the right of it because it has negative slopes. So if it was increasing coming from the left, and then it starts decreasing going to the right, we would say that this is a maximum. And again, your justification for that is that from the graph, values to the left of +2 are positive slopes. Values to the right are negative slopes. So that means it was increasing as the graph approached 2, and it was decreasing as it it moved to the right of 2. So that must have meant it hit a local maximum. Can't guarantee that it's global, so we have to just say it's a local maximum. So that answers the criteria for part C. Part D asks for you to find out values for which the graph of g has a point of inflection. So again, an inflection point is where the graph changes from decreasing slopes to increasing slopes, or you could say from positive to negative. So let's pull that graph up one last time here. I can't get rid of that stuff. Here's the original graph, and we want to find out where the slopes go from increasing slopes to decreasing slopes for g. And remember this, as we derived earlier, this is representing the derivative of that g of x function. So to the left of -4, we have positive slopes. The slopes are increasing is what we're more interested in. The slopes are increasing to the left of -4. The slopes are decreasing to the right of -4. So that is your justification for why x equals -4 is an inflection point. The slopes change directions. Another one is at -2. The slopes are decreasing to the left of -2. The slopes are increasing to the right of -2, and that is the fundamental definition of what an inflection point is, where the slopes, the rate of change of the slopes, where they change directions. The slopes were positive, then they were negative, so that's an inflection point. The slopes are negative, then they were positive. The rate of change of the slopes was negative. The rate of change was positive, so that is an inflection point. And then there's one more. Slopes were decreasing. Wait a second. No, they're still decreasing here. So remember, this one's not an inflection point because the rate of change of the slopes is decreasing. Rate of change of the slopes is still decreasing. It's just decreasing at a different rate. It didn't go from increasing to decreasing, so that's not an inflection point. But one I skipped over was at x equals 0 is an inflection point because the slopes are increasing. They're getting bigger. It's just at a slower and slower rate, and finally it stops, and now the slopes are officially decreasing. So if you make that your justification, that the slopes we're increasing to the left. The rate of change of the slopes was positive to the left of x equals 0. The rate of change of the slopes was negative to the right of x equals 0. And this is also an inflection point. Those are your 3 inflection points for part